Hi, just a quick video to show you a neat way that you can potentially reduce power consumption in your microcontroller products. And it has to do with the phenomenon called diffusion capacitance. And, well, we won't go into the whole physics of it because, well, yeah, it kind of is advanced semiconductor physics about how it all works. But you're familiar with the normal PN junction diode, of course, has what's called junction capacitance. That's also called transition capacitance or depletion capacitance. Goes by a couple of names, but everyone just calls it basically junction capacitance. And that's where a diode has a capacitance across it, effectively across its PN junction, but it actually has to do with the insertion of charges and things like that acting like capacitors. And there's actually quite a little complex formula, here it is, that actually has to do with that. So yeah, we won't go into details, but another aspect of semiconductors, and especially, is that a hair? Where did that come from? There's in particular CMOS processors like you're familiar with. Now, what I've got here is a typical, just a CMOS inverter here, and we've got our N-channel transistor and our P-channel here, and that simply forms an inverter. That's how CMOS gates are built, and you get multiple ones for those to create AND and NAND and NOR and XNOR gates and everything else that makes up your familiar micro controller these days. But anyway, here's a rough Dave CAD sketch of what it looks like on the the silicon level, the semiconductor level. Please excuse the crudity of the Dave CAD, didn't have time to build it to scale or to paint it, but basically we've got a P substrate down here, we've got an N type here, and this is our upper MOSFET up here, and this is our lower one down here, and these are the connections outside. So our input goes into the two gates here, didn't label those, but goes into the two gates, and then we've got our drain, our source, and our drain. Our two drains are connected in the middle like this. That's our output and source. But basically within the structure itself, you're actually going to have what's called diffusion capacitance inside, from source to substrate, drain to substrate, and the N-type to substrate as well. And once again, just like junction capacitance, it has to do with injection of carriers, your holes and your electrons, and all your semiconductor physics stuff that you groaned about when you learn that sort of stuff. But it has to do with minority carriers, and basically when these minority carriers are injected into the neutral regions, and once again it gets all complicated, but anyway, and then those carriers have to be removed to turn off the actual transistors, and of course they're switching all the time, and of course the processor contains like millions of these transistors, so they're all switching all over the place. So all these carriers are being charged and discharged into here, and it's not a linear type thing. It actually, here's the formula, it does actually vary with voltage, it varies with temperature, and it varies with current as well, and it's just, it's all over the shop. But anyway, there's capacitance inside the chip. That's what I'm saying. So we're going to actually use this diffusion capacitance to do a trick you normally wouldn't do, to actually pulse width modulate the power, the VCC up here, and rely on the internal diffusion capacitance in here to keep the processor running while you actually switch your VCC power supply up here. Sounds crazy, but it works. Okay, so what I've got here is an Arduino Uno compatible, the Freetronics 11. It's quite old, but it has a little prototype area, which I've used here. But I've added a power MOSFET up here into the VCC line. For those playing along at home, there's the part number DMP 2305. Don't know, just grabbed it out of the bin. Good enough for Australia. So I've connected the drain of that to the VCC here, and the gate I've actually connected over to D10 over here on the Arduino board. So then the software can actually switch on and off its own power and do that at the PWM rate, which I think is like 400 and something hertz or something like that for the Arduino Uno. And then on the top side here, I've actually removed the bypass capacitor here. I'll show you the schematic in a minute. And basically, I'm feeding the output of the MOSFET to the power pin, both analog and digital power. I've actually cut the trace down here. So this is the 5 volts going in to the analog VCC and the digital VCC up here. So we can actually whack a current meter in series with that and measure the consumption of the processor as we switch the the power. So you can see what I've done here. I've removed the 100N bypass capacitor because you don't want any bypass capacitors in the way. We're actually relying on the diffusion capacitance inside the chip to do the business. And we're inserting a diode here because we don't want to back power anything. We want to make sure, now I've done a whole video on back powering chips, haven't I? Yes, I have. I'll have to link that in. Anyway, don't want to back power anything. We want to make sure we're measuring the current going into the processor, and then it just connects through to here. So the processor's actually going to switch its own power, which sounds insane, but diffusion capacitance allows us to actually do this, and we're going to get reduced power consumption. It's neat. So I'm powering this just from an external USB pack here. I'm breaking in here with our current meter, which is our key site up here. And just to make it actually do something useful, I've got an LCD here. The LCD is not powered from the processor side of those tracks. It's powered from the header pins down the bottom, so that's not contributing to the power consumption. So if I switch that on, there we go. Bingo, we're in. It's just counting, so we have like, it's just doing something. It doesn't mean anything. And I can actually set with the switches here, the pulse width modulation value going to the pins. At the moment, it's 100%, so that chip is not switching. So the power is just permanently on. It's working like it normally is. And I'm also going to hook a scope across here. Okay, so at 100% PWM, you can see that we're getting, like, it's nothing, it's just permanently on. We're getting about 10.5 milliamps there, which is about right for an 16 meg AT 3 to bloody... that's my power bank. Let's see if it still works when we actually go down. There you go. I've just dropped it down. 96, I've just dropped it to X values. It's not a precise percentage, but there you go. Ta-da! We are now switching the... Oh, bloody touchscreens. 490 hertz. And the diffusion capacitance still allows this thing to work. We can see, it's dropping down a bit there, but it works a treat. And then if I change my PWM again, there you go, a bit bigger, 84%, it just gets bigger, but it's still working. So let's actually test this with the power consumption, 100%. Okay, there's no switching, but once you start switching that VCC line, it's lowering the power consumption, even though the 5-volt rail is still, you saw the waveform before. It's not like it's dropping it down to 3.3 or anything like that. The internal diffusion capacitance, which is making its way back out. But internally, it's actually, it's going to be significantly different to what we see externally on the scope. But look at this, it's still working. And we're lowering the consumption. Yeah, it's fairly linear. Look at that. So we've halved our consumption by PWM in this 50%. But depends on how much fusion capacitance you got in there, what voltage you're operating at, what temperature you're operating at, all that sort of jazz. It's going to come and get to a point where you can't PWM it anymore, and it's just going to come a gutser. Are we going to hit that? 25. Oh, I double bounced. No. Wait. No. Something's... No. No, it's Kamagata. Hey, no, it's Kamagata. It's starting to play up. No. All right. Yep. There we go. I managed to get... Yeah, it's random. Yeah, crap. So it's obviously, like, the processor's still doing stuff again, but, yeah, they're just garbage. They're not even... Are they part of the character set? I guess maybe they are. But yeah, you can really see some bizarre stuff, and it goes bonkers. As if you've ever tried to like set up an LCD and you get your one of these Hitachi ones and you get your drivers wrong and they just spew garbage into it and you get, garbage in, garbage out. There's a limit to this, so don't expect this thing to work in every situation. In fact, I wouldn't recommend you use this in a production environment, that's for sure. But who would have thought you can actually PWM a processor's own power supply? It sounds nuts, but it doesn't work. Kind of well. That's my bloody power bank again. And as I explained, this will not work if you put a bulk capacitance on here. It's just a silly idea to try and PWM the power of a complex device like this. It only happens internally with the magic of diffusion capacitance. It's good stuff. Linked in down. I'll link in some references down below. But it is an interesting phenomenon where you can actually PWM a processor to get reduced power consumption. Who knew? There you go. Neat, huh? Anyway, if you liked the video, give it a big thumbs up, and as always, discuss down below. Catch you next time.